So today we're going to talk about Chapter 14, Oscillations and Simple Harmonic Motion. Simple harmonic motion is a very common motion. We'll see a bunch of examples in the next couple of days. Basically, it's back and forth style motion, usually due to, say, a spring or some kind of restoring force. And so a block going up and down on a spring, a pendulum rocking back and forth, even atoms in the molecules when they vibrate are going back and forth. And so a real key point to simple harmonic motion is the restoring force of a spring that we've talked about. So the force due to a spring, right, we know that the spring really wants to get back to its happy point. Okay, so it likes to be over here. And so when you pull it out, it likes to get back over there. If you push it in, it likes to get back over there. And so this is the key motion to a simple harmonic motion. Okay, so that the spring is always wanting to get back to its happy place. And so as an example, let's say that we pull a spring out some distance here with a block on it. Well, what's going to happen is that block is going to bounce back and forth. And this motion is called simple harmonic motion, this oscillation. So let's think about this a little bit, exactly how this works. So here's a give it a try question. So what's happening here is, so suppose this hand here pulled the block some distance A from its happy point. Here's the happy point. And then immediately releases the block. Okay, and so let's define the positive x direction is to be this way. And so let's just say that once you let go of that block, I want to know is what would be the sign of the velocity and the acceleration for the block. Okay, so look over these answers and see what you think. All right, so for this one, the answers are velocity 0 and acceleration equal negative. Now this is a tricky one. The acceleration is going to be a little bit easier to think about. The spring force we know is pushing backwards this way here. So since the force is backwards like that, the acceleration would have to be that way too, in the negative direction. And the thing is when you put your hand here, right when you let it go, okay, the velocity is 0. The force is acting, it's accelerating, it's starting to move, but at that very instant it would be 0. Okay, so we're going to notice this trend here that when one of these guys is 0, the other one has a maximum value. The spring actually at this point is going to be the maximum amount of the force the spring has, because as it moves forward here, the distance away from the happy point is less, so the displacement is less, and so that force will get smaller. Okay, now let's try another one. So after the block has been pulled by the spring, so it's left the hand, it's been pulled back, and now the block and the spring are at their happy point right now, at the equilibrium length for the spring. I want to know what again is the relationship between the velocity and the acceleration, remembering that the positive direction is again to the right. Okay, so for this one, I get that the velocity is negative, so now this block is moving. Okay, so the spring had been pulling on it. It pulled on it to this point right here, okay, and the spring now has a really large velocity in the negative direction. However, the acceleration is 0. Why is that? Well, the force at that point is 0, right? When the spring is at its equilibrium position, k times x is 0, and so the force would be 0. And so, again, we find this relationship that the velocity is basically the biggest that it can be. All right, because what's going to happen now? Well, now if it starts moving a little bit this way, the spring will push back on it and start to slow it down. So the velocity is the biggest it can be in the negative direction. The acceleration is 0. So we notice this trend of how the velocity and the acceleration are kind of opposites. And so let's look at a little diagram here. Okay, so here's the block. So at the initial point, we're going to call the position positive A. So you pulled this block some distance. So this is the equilibrium position, this little x equals a 0 point. And then here you've pulled it out to some positive A. So at that point, the velocity is 0 and the acceleration is a maximum in the negative direction. All right. Now if we look at the next couple of positions here, now when the block is at the center point, we just talked about this, the velocity is its maximum in the negative direction, acceleration is 0, and the position is 0. So we'll notice something here that basically the position and the acceleration are at their maximum values when the velocity is at its minimum, and then vice versa. Okay, over here, the position and the acceleration are 0 when the velocity is at its maximum. And we notice this trend. If we keep going to the point where the block slides into the negative direction, okay, when it stops, its position will be negative A. That's the greatest displacement it has from the 0 point. The velocity will be 0 because it's turning around at that moment, and our acceleration will be maximum, again because the displacement of the spring over here is the greatest. And so we notice this trend, and if we just go through the next couple of them, okay, the same thing happens. So in simple harmonic motion, the velocity will be maximum when the position and acceleration are 0. And then the velocity will be 0 when acceleration and position are at maximum values. Now you'll notice that they're off by a negative sign, but they're still at maximum values. So these functions are related to each other, and we're going to talk about how that works. So let's describe this motion. So it's oscillatory motion, goes back and forth, and we're going to try to look at it and see if we can describe it with some kind of equations. So what function looks like this? Well, the sine and cosine function look like oscillations. Both functions go back and forth between 1 and -1. Now to make it easier, we'll just pick the cosine function to start with describing this. And so I'll talk about my position as being a times cosine omega times t. A is the amplitude, which is the maximum position. Cosine goes from 1 to -1, and so the maximum value of x would be a and then negative a. So it goes back and forth between a and negative a. And omega is called the angular frequency, which is in radians per second. We're going to talk a little bit about that and try to describe what that means physically, because I think that's tricky. And one thing to be careful about here is that this is in radians in this particular case. So if you're actually plugging in numbers into your cosine function, you've got to put your calculator into radians. That can throw you off. So here's just a little picture of just simple harmonic motion. Hopefully this is get caught up pretty well in the video, but you can see that what it's basically doing is there's a little pencil there, and it's essentially making a cosine function. So it's really nice how that works. So here's a cosine function. Again, it goes back and forth between 1 and -1, and a couple different things. If you're looking at the function versus time, which we are in this case here, then we can define what's called the period. The period is the time it takes to do one oscillation. And so here I went from the top peak to the top peak. You can go from any point to any point. I could go from right here to over here to where it's, these 2 points where it's basically repeating the same motion. That's also the period. So lots of ways to think about the period from a picture. So the period is the amount of time it takes to one complete cycle. The frequency is the number of oscillations per second. All right? And that's this f value. That's different than the angular frequency. And so we have these two things, and this is basically the two biggest things where you can describe simple harmonic motion. You describe it whether it's period or it's frequency. And the angular frequency is confusing, but basically all that it is it's just converting regular frequency into radians so that your cosine function knows what to do with it. Okay, so the omega is just 2 pi times your frequency. You can solve for different variations of that here. And what that does is when you have omega times time, which is inside your cosine function, you have radians per second times second. The seconds cancel out and you're left with radians. So literally, omega and frequency just describe the same thing, but they're in different units. One's in radians and one's not. So for our position function, if we just take an example, let's pick one, x equals 5 times cosine pi over 2 times time. And if we just plug in values, here at 0 time, it would be 5 meters. Here at pi over 2, so at time equals to 1, it would be pi over 2, it'd be 0. Okay, and we can just keep plugging in values. Time equals to 2, it'd be cosine of pi, so we get -5 if you plug this in. Remember, if you're plugging this in at home, make sure it's radians. Your calculator is set in radians. And so basically we just plug in all these different seconds, and we see that the pattern does repeat. Okay, this cosine gives us an oscillatory function, just as expected. Okay, let's try another give it a try question. Here's a graph of the position versus time for some object in simple harmonic motion, and we want to know what is the angular frequency of this object. Okay, so hopefully you got C. And basically the way this works here is you can get a relationship between angular frequency and period. In this particular graph here, you can get the period. The period is the time to do one oscillation, would be 4 seconds. And so plug that in, you can solve your angular frequency. Now velocity, in simple harmonic motion, the object's velocity will oscillate as well, and it has the maximum at the opposite times than the position does. And so if this is our position function that we picked, the function that will actually have the opposites would be the sine. Okay, the sine function will be hitting 0 when the cosine function is a maximum, and vice versa. So sine has a max value and cosine has a minimum value in general. This V max is the maximum velocity, and if you solve for it, you get an equation which is omega times A, which, if you figure that out, has units of meters per second. And so our official equation would look something like this. So if your position equation looks like this, then your velocity equation would be a sine function. Again, omega is the angular frequency. Okay, let's try another, give it a try here. So it's the same situation we were talking about before. I want to know is, what is the magnitude of the speed of the object at time 2 seconds? All right, and hopefully we got this one here, 0.13 meters per second. So the trick here is just realize, okay, so here at time 2 seconds, the position is 0. So we know that if the position is 0, the velocity is hitting a maximum. And our velocity maximum equation looks like this here. So it's omega, the angular frequency we found in the last problem, times amplitude. And amplitude is basically the maximum displacement. And so here that would be 0.08. And so those two together give us C for the choice there. And so our finally one that we're looking for is acceleration. We know that this is going to then again have the opposite of the sine, but if you remember, it was basically the same as the position. And so the function that does this is cosine, but remember there was that pesky negative sign. And so the acceleration is negative the acceleration max times cosine of omega t, where A max is the maximum acceleration. If you figure out the maximum acceleration, we get this equation here, which will have units of meters per second squared. And so our function looks kind of like this when you plug everything in. So it's a cosine, just like the position. That's why the position and the acceleration are peaking at the same time. All right, let's do another give it a try. So now I want to know is, what's the magnitude of the acceleration of the object at time t is equals to 2 seconds. Okay, and hopefully you got that it's 0. So again, the position is hitting 0 at 2 seconds, so that means the acceleration will also be hitting 0 at times 2 seconds. So here's our equations for simple harmonic motion the way we set it up. Now the thing is, in the beginning we picked cosine just because we liked it better than sine, but you could have done this same thing with sine. Okay, and so here's the same thing starting with the sine function. All right, so that would be simple harmonic motion where basically at time 0 you're starting at the 0 position, which could be happening. Okay, it just depends on when you decide to start your time 0. All right, and here's basically a bunch of information that we have been figuring out about simple harmonic motion. And this one actually we haven't talked about, so try not to look at that. So here's an example. So an object experiences simple harmonic motion. It's got an equation there, given in the equation, and we want to find out a bunch of stuff about it. So what is the period of oscillation? Well, period is 2 pi divided by omega. Omega is what this 30 is. Okay, if you look at our equation, it says cosine omega times t. So you plug in this 30 for omega, you get that the period is 0.209 seconds. To find the velocity maximum, it's omega times A. Again, omega is 30, and A is the amplitude, which would be this 2 meters. So you get 60 meters per second. The maximum displacement of the object is just the amplitude, so it's plus or minus 2 meters. And then to find the maximum acceleration, it's this equation, omega squared A, and you get 1,800 meters per second. Now, one thing I wanted to mention real quick, just about what Knight's doing here is, so like we mentioned, you can pick the cosine or the sine function, but we can also do, and this is what Knight does, is introduce what's called the phase constant. All right, and that's this little symbol that looks like this here. All right, this guy here, and it's inside this cosine. And basically what that does is it gives you the flexibility to start your time or your oscillation any place you want. Okay, and they have this little graph here where they're basically talking about that here. Okay, and so we were starting, if we put in the cosine, we were starting with a phase angle of 0. And so if that was 0, and then you plug in times 0, then the cosine starts x equals to A. Now, if you put in that phase angle, that means when the omega times t is 0, you still have this phase angle, and so you're not starting at true cosine of times 0, you're starting at some other position. And so this kind of just gives you the flexibility to start anywhere you want in your rotation. So with the cosine and the sine, we're basically either starting at 2 points, but here we can start at any point we want. Okay, see you in class.